Okay, everyone, so this is section 1.8, and we're talking about combinations of functions and composite functions. So what's our objective is to add, subtract, multiply, and divide functions, find the composition of one function with another, and then to use them to model and solve problems. The cool thing about arithmetic combinations of functions is that just like how numbers that we know can be combined by adding, subtracting, multiplying, and dividing to make other numbers, functions can be combined to create new functions. Functions can be added, subtracted, multiplied, and divided, just like how numbers can. Of course, you have to make sure that you obey the laws of algebra. So let's say, for instance, you have a function 2x minus 3 and x squared plus 1. You can combine them to form the sum, difference, product, and quotient. So say here, all I'm doing is just adding them together, and that's what the symbol, like the symbolism, like the symbols used to indicate addition is right here. So you have 2x minus 3 plus x squared minus 1, and that becomes, when you combine like terms, x squared plus 2x minus 4. We can take the difference of functions, so f minus g. So you see f minus, and then in parentheses, make sure that whatever you're subtracting by is in parentheses, so that you can distribute the negative and make sure you have the correct answer. So you'd get negative 3 plus 1, which is a negative 2, negative x squared, and a positive 2x. Then you can multiply. So when you take the product of these two, it would be you can do FOIL or you could do box method. But this is what your result would be, 2x cubed minus 3x squared minus 2x plus 3. And then when we take the quotient, it's just one on top of the other. And we have, of course, the restriction on the domain where x cannot be plus or minus 1. So we make sure that we have, when we're combining functions, in particular when we're dividing functions, that our quotient, our domain is okay, because we cannot divide by 0, so then we need to consider that. Okay, so some more, just to restate what I've said, when you take the sum f plus g of x, it's basically what you're doing is you're taking the function f and you're adding the function g to it. When you take the difference, so f minus g of x, that's a whole other function which consists of the f function being subtracted by the g function, and then the product looks like this, so f g of x, and then you have f of x times g of x, and then quotient similar, f over g of x, where you have the function f of x divided by g of x. And then of course with the restriction that g cannot be 0. Okay, so let's do another example. Suppose you have f of x is 2x plus 1, and g of x is x squared plus 2x minus 1. Then let's find the sum, and then let's evaluate the sum when x is equal to 3. So let's take the sum of f and g is f plus g of x, which is f of x plus g of x, which is 2x plus 1 plus x squared plus 2x minus 1. And then if we combine like terms, well, x squared doesn't have another term, so then we have 2x plus 2x is 4x, and then we have 1 minus 1, which is 0. They cancel each other out. So when you have x equals 3, the value of this would just be 3 squared plus 4 times 3, which ends up being 9 plus 12, which is 21. So that's an example of that. Okay, so composition of functions. So composition of functions is super fun for me. Thing that I think is really cool. It's basically when you're basically taking one function with the other and we compose them. So in other words, you have an inner function and you have an outer function. So let's say you have f of x is x squared and g of x is x plus 1. The composition of f with g, or you would say here, see, notice that g of x is your inner function. So basically, it's where the input of f is an actual function. Okay, so you're saying, what is f of x plus 1? But what's f? F is telling you, hey, whatever you put inside of me, square it. So in this case, we're putting in g of x, which is x plus 1. So then we just square it. So then the way that we write this is little tiny circle like this, f of g, and we read f composed with g. Okay, so the composition of the function is f of g of x, which is f composed with g, or f of g of x. Okay, so that's the set of all x. It's in the domain of g, such that g of x is in the domain of f. So we have here our inner function. We have g here, we have x, we have g of x, and that's the domain of f. And that's kind of how we think about the domain of f and g. Okay, so let's go ahead and do a couple of examples, right? So if I were you, I would pause right now, I would try to work these out, and then I would check answers with me. So first of all, what was the first one? It was f of g of x, right? So f was x plus 2, and g of x was 4 minus x squared. So my input is g of x into f, right? So this is inner and this is outer function. So we have 4 minus x plus 2 because that's the definition of f of x. And so if we simplify this, we get negative x squared plus x. Okay, secondly, we have g of f of x, where now the inner function is f and the outer function is g. So now make sure you understand this carefully. The input of the function g is an entirely, is now f. And what is f? F is x plus 2, yeah? So x plus 2 goes into g. But what is the rules of g? G tells us, hey, whatever you put inside of me, let's take 4 minus, let's square it, subtract it from 4. So we put inside g x plus 2. And then we square that, and that gives us x squared plus 4x plus 4, and we're subtracting that. And when we combine like terms, we get negative x squared minus 4x. So in this case, f, notice that it's not commutative. Composition is not commutative, like not always. F of g of x does not equal g of f of x. Okay, so then next, using that result of part B, we just plug in negative 2, I'm sorry. So we get a negative of negative 2 minus 4 times negative 2. So that's negative 4 plus 8, and that's just 4. Okay, so an example, so we did this composition of two functions, and oftentimes it's important to be able to identify, in calculus, you are definitely going to need to do this, be able to identify the two functions that make up a composite function. So the function h of x is equal to 3x minus 5 cubed is the composition of f of x, which is equal to x cubed, and g of x is equal to 3x minus 5. So therefore, your inner function is going to be this 3x minus 5, and your outer function is going to be x cubed. So then you have g of x quantity cubed, so therefore you have f of g of x. Next, so then let's say to decompose a composite function or a composition of functions, we look for inner and an outer. That's exactly what I just said. Okay, fine. So now we have some exercises. So let's say here, can we use a graph to show that, to graph the sum of f and g of x? So it's very simple. So here, by definition, h of x is equal to f of x plus g of x. But bonus points to you, brownie points to you, if you remember, what does f of x symbolize? So remember, if you can recall that f of x is equal to y, right? It's the y value, the value of the function. So here, the value of the function f is 2, and here the value of the function g is negative 1. So what's 2 plus negative 1? Well, that's just 1. Okay, so see how we're doing that? So then here, the value of f is 3, the value of g is 0. 3 plus 0 will be 3 at the x equals 1. So then here, at x equals 2, we have the value of f is 1, and the value of g at 2 is 1/2. So then here, h would be 1 1/2. And then finally, we have 2 and 0. So then the value at 3 will be 2 for H. Okay, and then here we go. Here's another example in the homework, I think. We have f of x and g of x where we add them, f plus g of x, f minus g of x, the product, and then dividing, right, or f over g. But since these are rational functions, it's easier for me to write them this way because then I can flip and take the reciprocal. The only difference is that for f over g, which is d, we need to state clearly that x cannot be 0 because that was f, g and f are both restricted in the sense that x cannot be 0. So therefore, the quotient of them cannot have x as 0 also. Okay. Yep. And then what was I going to say? Oh, all we did for a and b, we're doing common denominator. So we multiply top and bottom by x here in the first term and here as well. And then here we just multiply straight across. Okay, that's it for this section. 1 through 45, every other on. Good luck, happy studying, and I will see you in the next video.